Sample problem 21.5 introduces the concepts that there's relationships between three parameters that we've learned about. Again, we learned about delta G in chapter 20 on thermodynamics. We learned about K beginning in chapter 17, equilibrium constants, and we had 3 chapters that we dealt with equilibrium constants. And then in this chapter, we just learned about E cell. And so this problem reminds us that there are ways to walk between all 3 of these parameters and equations to walk between all 3 of them. The equation that we learned in chapter 20 to walk between delta G and K is that delta G equals minus RT ln of K. 2 new equations will allow us to walk between E cell and K and E cell and delta G. The equation that allows us to walk between free energy and E cell is delta G equals minus NF E cell. And just to remind us here, N is equal to the number of electrons in the redox process. And this has to do with the number of electrons exchanged. So we're not going to add, 2 electrons from the reduction and 2 electrons from the oxidation and get 4. The number of electrons participating in the redox process in that case would be 2. F is Faraday's constant, and so that's 96,485 joules per mole volt. Okay, so that's just a constant. The R is the same R constant that we've been using, 8.314 joules per mole Kelvin. The equation that we can use to walk between E cell and K is E cell is equal to RT over NF natural log of K. And one of the things that we can do here is if we are at 298 K, which is common when we're talking about standard conditions where we're going to be at 25 degrees Celsius, is we can combine a constant temperature then with R that's a constant, F that's a constant, and we can actually use a factor of 2.3 to interconvert natural log and log base 10, and we can make this basically be a constant, which is going to be equal to 0.0592, and this equation can be a little bit more simple, and we can have that E cell equals 0.0592 volts over N times the log, log, of K. So in that case, you only have one thing that you need to consider, and that's the number of electrons that are being transferred. But the only time, again, you can use that simplified equation is if you are at 298 K. So this problem would be really straightforward if it told us what E cell was for this process. But because it doesn't, it all of a sudden becomes like sample problem 21.3 or 21.4 or our in-class problem where we actually have to figure out what E cell is. So we're going to go through that pretty quickly because, again, that's something that we've done before. If you need to review how to calculate E cell, again, go back and look at the in-class problem on calculating E cell. So to calculate E cell, we have to figure out our 2 half reactions. Again, we can, since we're given this overall reaction, we can see that lead is being oxidized. So we can get the oxidation potential here as positive 0.3 volts. Silver is what's being reduced, and I'm already going to scale this because I know I have to have my number of electrons in my reduction equal my number of electrons in my oxidation. That does not change our standard reduction potential value. That's 0.8 volts. Sum these up, and we do get the equation that we see above. And then E cell is really the sum of these 2 values. So that's going to be positive 0.93 volts. So now that we have this, again, we have this parameter. This problem asks us to calculate delta G and K. I'm actually going to go, remember when we had our around the block that we do with pH, POH, H3O plus, and OH minus calculations. I'm going to show you that we're going to go from here to here and then here to here. And once I get this value using this new equation, I'll show you that it's the same as if we would walk from K to delta G using the equation that we had from chapter 20. So I'm just going to grab a new piece of paper so I can put all of this kind of on the same sheet here, but I'll keep my equations kind of up here so that we can see them. E cell was, again, positive 0.93 volts. So I'm going to take this walk first, okay? And this tells us, I didn't read the problem up here, this problem tells us that we want to consider it at 298.15 K, which means I can use this simplified version of this. So E naught cell equals 0.0592 volts over our N is our number of electrons. We could see that there was 2 electrons that were part of this process. So over 2 log of K. So we've got positive 0.93 volts equals 0.592 volts over 2 times log K. Let's see, we can probably just start with this. We know that E cell is 0.93 volts. So mathematically what you end up getting is 31.4189 equals the log of K. So K equals 2.6237 times 10 to the 31st. And again, hopefully that makes sense. We had an E cell that was spontaneous. Spontaneous reactions also mean a negative delta G. Reactions that have negative delta G's means that we're going to be product favored, which means we should have a large equilibrium constant. So what I'm going to do now is I'm going to take this, I'm going to use our delta G equals minus RT ln of K to get our delta G value. So delta G, again, equals minus R T times the natural log of our K, 2.6237 times 10 to the 31st. Delta G in this is going to equal minus 179.3 kilojoules per mole. Okay, what I want to do now is just convince you that we took kind of 2 walks through here. We started with E cell, and we used a new equation to get us to K, and then an old equation to get us from K to delta G. That was our old equation. What I'd like to do is use a new equation to walk E cell to delta G. So delta G equals minus NF E cell. So in that case, delta G is going to be equal to minus 2.96485 joules per mole volt times our E cell, which is positive 0.93 volts. And in this case, delta G will equal minus 179.5 kilojoules per mole. So within experimental error, these guys are the same value. So pretty straightforward problem in sample problem 21.5, just understanding that there's 3 equations now that allow us to walk between E cell, equilibrium constant, and free energy. Again, all of these really relating to the spontaneity of a reaction.